In this video, we're going to talk about seafloor bathymetry. This is an important concept before we talk about seafloor spreading and continental drift theory. Three-fifths of the Earth's surface is under the ocean, and the ocean floor is as rich in detail as the land surface with which we are familiar. So what would the ocean floor look like if we drain away all the seawater? So this animation simulates a drop in sea level that gradually reveals this detail. So as you can see, as the sea level drops, the continental shelves appear immediately. They are most visible by a depth of 140 meters. The mid-ocean ridges start to appear at a depth of 2,000 to 3,000 meters. By 6,000 meters, most of the ocean is drained except for the ocean trenches. So the question is, what do you think is the reason why the world's water supply is shrinking?
Well, I don't know, darling. What do you think?
Okay, so let's talk about that first, right? It's like a paradox. So our water supplies are shrinking, but at the same time, the climate change is generating more intense rains. Also, the ice or the glaciers are melting. But why is the supply of water shrinking? Researchers from University of New South Wales believe that the cause is the drying of soils in our catchments. So soils were once moist, so when it rains, the wet soil allows rainfall to run off into rivers. But now they are drier, so they soak up more of the rain and less water makes it as flow. Okay, so there's no runoff. So how do scientists study the seafloor?
Yung makapag-isip, wait.
The seafloor is the solid surface underlying a sea or an ocean. One misconception is that seafloor is flat or bowl-shaped, and the deepest portion is in the middle. Now, we can't really drain the water for us to study it. But how come scientists have information regarding the seafloor? In this lecture, we're going to study what the seafloor looks like. To do that, we need to study bathymetry. Bathymetry is the study of underwater depth of ocean floors and lake floors. In other words, bathymetry is the underwater equivalent to hypsometry or topography.
I didn't get that.
Prior to the 1940s, very little was known about the deep oceans. During the World War II, with the advances in electronics and sonar, it became technologically possible to map the ocean floor in great detail. One technique used by mariners or scientists is the sounding line. It is consisted of heavy weight hanging from a long string that was lowered into the ocean until it hit the bottom. So the amount of string lowered is equal to the depth of the seafloor. So the problem is, currents could carry the string away from vertical or the weight could be snagged by debris, making the seafloor seem deeper than it is. The biggest issue with the sounding line technique is that resolution is very low. So meaning it is inefficient to take enough measurements to make a very detailed map. This is an example of the number of measurements made using the bathymetry. Okay, so this is the bathymetry map of Walden Pond. Next, we have sonar or echo sounding. This is the most common method for mapping the seafloor. This figure shows a cartoon illustrating how ship-based sonar collects data. Sonar is a sound energy that is transmitted by an instrument on a ship called a transducer. So it travels through the water, bounces off the seafloor, and returns to the ship where it is recorded. The amount of time it takes for the sound to return to the ship allows scientists to figure out how deep the seafloor is. The area covered by one ping of energy is a thin patch of seafloor called swath. The figure on the left is a detailed map of the Peru-Chile Trench made with sonar. The figure on the right is just a map of the Chilean coast. The problem here is that ships must travel above the area being mapped, and the ocean is a large area to cover. But the advantage is sonar mapping creates very detailed images. Next, we have satellite altimetry. So this figure shows how it happens. This method profiles the shape of the sea surface by measuring the travel time of a radar pulse. So the shape of the sea surface approximates the shape of the sea floor. So just remember, altimetry shape.
Thank you.
There are many different types of features on the seafloor, and the depth of the seafloor can be anywhere between sea level and about 7 miles deep. Note that this figure has a large vertical exaggeration, so meaning that the vertical scale is stretched significantly. Basically, the vertical features are not actually as tall or deep as they appear compared to a real-life situation. So the first feature is the continental margin. It's the submerged outer edge of the continent where continental crust transitions into oceanic crust. Now, there are two types of continental margin, the active and the passive. So the passive type is also called the Atlantic type. So it features a wide, gently sloping continental shelf, steeper continental slope, and a flatter continental rise. Continental shelf is the one that's semi-horizontal. Slope is the steep area between the shelf and the main part of the seafloor. So it is important to take note of their depth because it's unique for each part.
Okay, okay.
Continental shelf, 50 to 200-meter depth. Slope 3,000 to 4,000 meters depth. Now, the active type is also called the Pacific type. It is characterized by a narrow shelf and slope that descends into a trench. Another important note to consider is that this diagram is a passive continental margin. Next, we have the abyssal plain. The abyssal plain is the wide area between the continental slope and the trench. It is extremely flat, sediment covered that stretches off the ocean floor. Okay, so it contains many features such as guyots and abyssal hills. It is interrupted by occasional volcanoes, mostly extinct, called seamounts. So later we will discuss them. Abyssal hills are most commonly caused by blocks of oceanic crust that has been faulted and tipped at an angle. Remember that abyssal hills are the most common seafloor feature, but they are often blanketed in a thick layer of sediment to the point where they become invisible. Interrupting the abyssal plain is a mid-ocean ridge or oceanic ridge. This is a long underwater mountain chain that connects all of the world's ocean basins. It is the longest mountain chain on Earth. It has a central reef valley and rugged topography on its flanks, so they are cut and offset at many places by transform faults. Next are the oceanic trenches. Okay, oceanic trenches are the deepest feature of the ocean and they occur closer to the margins of the ocean basins. So meaning the seafloor is not in the center of the ocean. Okay,
Okay, and what do you want me to do about that?
so that's one of the misconceptions. Finally, there are also seamounts of various kinds, which will be explained more later. So some seamounts can be so tall that they emerge above sea level and form islands. To make it easy, submerged volcanoes are called seamounts, while those that rise above the ocean surface are called volcanic islands.
Can I get a wow? Wow! Can I get another wow? Wow! Give me another one. Wow! Call the ambulance. Wow!
So there are many volcanoes in various stages of evolution that pepper the seafloor. Okay, again, a volcano that does not reach sea level is a seamount. A volcano above sea level is an island. An island that has been eroded flat and submerged is a guyot. So the bottom images are bathymetry maps of different types of underwater volcanoes. Now, in the next video, we're going to talk about seafloor spreading. So make sure that you click subscribe. What?
What else?